In this video, we're going to look at a heating curve. Okay, a curve is just a fancy word for a graph. So essentially a graph of how something changes as heat is added. So we're going to have temperature on this axis, which seems like a pretty reasonable thing to put on there. You know, if heat is being added or removed from something, likely we're going to see some kind of temperature change. We will also have along the x-axis here, as heat is added, how much time goes by. Okay, so this is going to be basically heat added constantly, like if you were to put something on a hot plate or a stove or over a Bunsen burner, okay, kept at the same heat, not cranking it up and turn it down, back and forth the whole way through. We're just keeping it one consistent kind of level of heat being released over time, and time's going to keep moving this way. Let's add that in. Okay, so this will be time in minutes as heat is added, done this way. Okay, and we're going to start with a solid. Okay, in this case, our substance is going to be water, but you can make a heating curve for just about any substance. Okay, specifically, we're going to start at a very low temperature. Okay, so this is going to be the very cold, solid version of water, ice. Okay, so we're going to start down at a very low temperature and start working our way up and adding heat as we go this way. Okay, now again, we're starting with just the solid. And as we add heat to the solid, the particles in the solid are going to move faster and faster and faster. Okay? What we measure as temperature is really the kinetic energy of those particles as they move around. Okay? So as they move faster and faster, that means they have a higher kinetic energy, which we feel as a higher temperature. Okay? And what your thermometer will measure as a higher temperature. So temperature is kind of the macroscopic, the big scale way of figuring out how all those little particles are moving. Now, we don't care about any specific particle, so technically we look at the average kinetic energy of all the particles in a sample, like this piece of ice in this case. So you can think of the temperature scale as essentially just a measure of the average kinetic energy of the particles that make this thing up. Okay, so although our temperature scale is in degrees Celsius, you can also think of that as how we're measuring average kinetic energy. It's kind of proportional in sort of the same way. Okay, well, as we keep adding heat to this solid, to this ice, okay, it's going to keep increasing in temperature until we hit a certain point where it does something a little bit curious. When it hits 0 degrees Celsius, it stops changing temperature. It stops getting warmer. Okay? Instead, it stays at the same temperature. It kind of sticks around there for a while. Okay? At this temperature, we start to go through a phase change. Okay? We're changing from one phase of matter to another. In this case, we start to form the liquid out of the solid. So while we're on this kind of segment here, we have both the solid and liquid present as we change the solid into the liquid. So we go from having all solid to more and more liquid instead as we go across that line. Okay? We are stuck at 0 degrees Celsius as long as we are still changing some of that solid into the liquid. And we only start increasing the temperature again once we have only liquid there. Okay? Again, this whole time we are adding heat. Okay, and yet our temperature doesn't start rising again until all of our solid is gone. Okay, so our temperature rises from here, right? And at this point we have just the liquid. All All right, so our liquid water gets warmer and warmer and warmer, okay, until it hits another flat point, okay, at 100 degrees Celsius. So again, curiously, even though we're continuing to add energy, the temperature doesn't go up, at least not for a while. We're going through another phase change here, okay? We are changing now from a liquid into a gas. So along this line, we're going to have both a liquid and a gas present. Okay, so we have both a liquid and a gas, right? Kind of like with this line before, once we hit a certain point where we have changed all of the liquid into a gas and there's only gas left, our temperature starts to rise again. And then it can go up and up and up from there. Well, this is interesting, okay? To figure out why we have these flat points, we have to think in terms of the particles and what they're doing, okay? And what that energy is really being used for, okay? As they absorb heat, what's going on there? So first off, we're starting with the solid. We get it warmer and warmer. We keep adding heat. Okay, that moves those particles faster. That's why we have a higher temperature. So really, we are increasing kinetic energy. And I'm going to abbreviate that with KE to make it a little bit quicker to write. So all through this first segment, kinetic energy is increasing. KE is going up. Okay, now on this next segment, if kinetic energy were still increasing, that would mean temperature would be increasing, because that's all temperature is particles moving faster and faster, slower and slower, whatever. But it doesn't change. So what is that heat being used for? We are still adding heat here. So if we're not increasing kinetic energy, the other thing we could be messing with is potential energy. Now you can kind of think of potential energy as the potential to move. In this case, we're dealing with particles that are attractive to each other. They have electrostatic forces that make them sticky and kind of, clump together. Okay? So that attraction pulls particles together. If we put in energy, we can pull them apart. And that's what's going on here. We are pulling particles apart. So that heat we're adding is being used to increase potential energy instead of kinetic energy. You can think of potential energy essentially as how we pull those particles apart from each other, how we space them out more. Think of potential energy as increasing the spacing here. Okay, so we continue to increase potential energy as we spread the particles apart more and more. Our solid, is now working its way out into a liquid where the particles can roll around, move past each other, rotate, until we basically spread out all that we can for this much energy. Okay? Once we have changed all of our solid into a liquid, then our liquid can start moving faster and faster and faster again. That heat starts being used to increase the kinetic energy. So once we have just the liquid, we start increasing the kinetic energy of the liquid instead. Again, we're going through the same kind of process. We're going to kind of hit a pattern here. Okay? So our liquid starts getting warmer. The particles are moving faster and faster and faster. Okay? Until we hit this other flat point again. Okay? Well, maybe it's similar to this. We're still adding energy, but our temperature isn't going up, so we can't be increasing kinetic energy. We must be increasing potential energy. We're pulling the particles even farther apart than they were before. So, those particles are no longer going to be in the liquid phase. They're going to be even farther apart in the gas, where they're just zipping around in all directions. Okay? They totally break free of those attractions to each other. So, once all of our liquid has changed into a gas, we have just a gas left. Okay? Which can continue to be heated, move those particles faster and faster and faster, which means kinetic energy is increasing. Okay, so we've got an idea of how our stuff changes as we continue to add heat and what that means for the energy of the particles. But there's still more we can kind of add to here. We can still add some detail and flesh this out a little bit. Okay, so first of all, we have some specific names for the phase changes that happen here and here. Okay, when we go from a solid to a liquid, we call that melting. Over here. Okay, and when we change from a liquid to a gas, we call that boiling. So, on these two segments, here and here, this is a phase change, and this is a phase change. Okay? Now, the temperature that they have, that these occur at, also have a specific name. Since melting is happening at this specific temperature, we call that temperature the melting point. Okay? And the temperature that boiling happens at is called the boiling point. Okay. Pretty self-explanatory. For water, the melting point is 0 degrees Celsius, and for water, boiling point is 100 degrees Celsius. Okay, that's getting closer. Now, to add to this a little bit more, these phase changes, okay, can also be described by how we are moving around that heat. In this case, in order to melt or boil something, we need to add heat in to the substance. So if we are adding heat to make this change happen, okay, we have a special name for this kind of phase change. We call it endothermic. These are endothermic phase changes. Okay, so heating curves show endothermic phase changes. Now, endothermic sounds kind of like a scary word, but it's really not all that bad if you break it down. Okay. Thermic just means heat. And endo just means in. Move this out of the way. Scooch this down here. So thermic is heat. And endo is in. Endothermic just means heat in. So we are taking heat in. We are absorbing heat in these phase changes. Okay? Cool. A bit of terminology. Okay, I think there's one more thing we can add to this, okay, and that's another fancy word. And it's used to describe when we have a couple phases of matter hanging out together at the same time. Okay? When you have phases of matter coexisting, like the solid and the liquid during the melting process, or the liquid and the gas during the boiling process, we say that they are in an equilibrium with each other. You've probably heard the word equilibrium somewhere, and it usually has something to do with a balance, or a sense of stability. You're in equilibrium or something like that. So in this case, we have kind of a balance between the solid and the liquid. They're hanging out together. Okay, so we have an equilibrium between the solid and the liquid during the melting process. And we have an equilibrium between the liquid and the gas during the boiling process. All right, so those are in equilibrium with each other. So a heating curve can tell us a lot of information about how a substance changes as we continue to add heat to it, usually at a steady rate over time.